हाय एवरीबॉडी। जैसे कि पहले दो सेशंस छोटे छोटे दो वीडियोस इलेक्ट्रोस्टैटिक्स के वहाँ पर हम लोगों ने देखा था कि व्हाट आर इलेक्ट्रोस्टैटिक चार्जेस, हाउ आर दे प्रोड्यूस्ड, व्हाट इज द बेसिक लॉ गवर्निंग द फोर्सेस बिटवीन the two or any number of charges, and that was Coulomb's law. After considering Coulomb's law, we understand that it's a force acting between two charges. If you have three charges, there will be, you see, pair of any two, and the forces will act on it. But force being a vector quantity, you just cannot add the magnitudes of forces. The forces acting on a single charge because of multiple charges surrounding it, they will have to be added by its vector form. So I need to take into consideration the vector effects of the force, or vectors, force as vectors, and I will have to do their vector addition. So what I find here in this diagram on the right hand side is that I have got a charge plus q1 shown over here, and then it is surrounded by some more charges q2, q3, q4, q5, out of which I find q2 is positive charge, q3 is a negative charge, q4 is positive, q5 is considered to be negative charge, such that there will be a force of repulsion acting between q1 and q2 along the line joining q1 and q2, that's F12 as shown in this direction. Q3 and Q1, they will have a force of attraction, and Q1 will then be moving towards this Q3 direction. It will have a force acting towards this line. Q4 will have a force acting away from that Q4, Q1 line, and Q5 will have a force acting in this direction. So, in fact, my total force acting on this charge Q1 is supposed to be the vector addition of this F12 plus F13 plus F14 plus F15. So if I add all these terms vectorially, then it will give me, or rather if I resolve those forces into their different components, or maybe separate and try to find. So in this case, vector laws of addition are effective. As you see, you are having more and more number of charges, the system will go on becoming more and more complicated. Rather, if I have three charges, what's going to happen is that when I take into consideration the force acting on Q1, I just have to consider the forces acting on Q1 and their vector addition has to be done. Whereas you cannot have, or rather we should not think about whether there will be a force acting between Q2 and Q3, Q3 and Q5, Q4 and Q3, Q4 and Q2. Yes, there is going to be a force acting on each and every pair in the system. But when I want to find the forces acting on Q1, I have to take the pair of Q1 with some other charge, and all those pairs, their forces, they will be taken into consideration, and its vector addition will give me what is my resultant force acting on Q1. Well, so that is how you can put it in the simpler manner, and in order to find the vector sum of two forces, you can actually use parallelogram law of vector addition. That is one of the best laws to find what is the vector sum of and what is the magnitude of vector sum of the forces. Now, what we are going to talk about next are what is meant by electric lines of force. This is a very important concept, as we have already talked about what is meant by you can say electric field. When I talk about electric field, I imagine some conceptual field, some virtual field around each and every positive or even a negative charge, where we have considered that electric field is radially outward due to a positive charge and electric field is radially inwards due to a negative charge. What governs or what makes this electric field? Then Faraday explained electric field in terms of electric field lines or electric lines of force, which have got a similar kind of properties to that of your magnetic lines of force, as explained by what we call it as Faraday's magnetic lines of force. Then, here in this case, what exactly do I understand by an electric line of force? It's of course an imaginary line, which may be straight line, which may be a curved path, along which a unit positive charge is supposed to move when it's allowed to move freely in the electric field. In fact, you have to keep a check on the charge, its motion, because if you just allow the charge to be in motion, it will have a tendency to move along its tangent. So the real electric lines of forces, they will be different as compared to, you see, your motion of the path of a test charge. Even if you don't understand this, what you just have to consider is that when I want to trace the electric line of force in a given electric field, you should not allow a movement of that test charge over a large distance. That is what the idea is. Now in this diagrams, you consider this left hand side diagram where your charge Q at the center is considered to be a positive charge. On the right hand side diagram, we are considering charge Q to be a negative charge, less than 0 is shown here. And on the left hand side, because my charge is positive, I am showing all my electric field lines to be in the radially outward direction. And it is not that there are only, you see, 3 plus 3 plus 2, that is only 8 lines of forces are existing. It is not that. These lines of forces are purely imaginary. They are only for us to understand. Further, what I need to understand is that whatever is the strength of electric field at this point, this point, this point, this point, this point, all these electric fields will have equal values because they are all at equidistant points from the charge Q. Whereas all the exterior points to that, all those points which are away from that, they will be having less value of electric field intensity. The same is the story on the right hand side diagram as well. So all those points which are at equal distance from the charge, this or this, they will be having equal magnitude of electric field and equal electric potential or equal voltage. So all such points, they are called as equipotential points. We will speak about equipotential points later on. The arrow is indicating, so you see, first one is the size of the arrow represents the strength of the electric field. The arrow size keeps on decreasing gradually, so electric field keeps on decreasing gradually. These arrows, they are marking whether that's radially inward or radially outward. Then second property of electric line of force is showing you that you see plus Q and minus Q are these two charges here. Here you have plus Q and plus Q, these two charges over here. So this system shown on the left hand side is basically an electric dipole where you have got two charges plus Q and minus Q which have got equal magnitude but exactly opposite sign. They are placed by a certain distance apart from each other, and on the right hand side you have got equal charges plus Q and plus Q. They are separated. Here I find that between this, on this right hand side diagram, plus Q and plus Q, in between these 2 points, the exact midpoint which comes here is named as N. That N is an electrically neutral point, you can say. Why is it an electrically neutral point? Because from this plus Q, whatever are the electric field lines moving towards downward direction, the same value of electric lines of forces are also moving in the upward direction. These lines, they cancel each other's effect. The total electric field at this point in between, that is going to be 0. Whereas if I take into consideration here at this particular point, this point will have an electric field acting downward because of the upper charge plus Q and also downward electric field due to minus Q. So the resultant electric field at this particular point will be twice that of the electric field produced because of either plus Q or minus Q. So that's what we need to understand. Then of course these are showing some diagrams what kind of electric field lines are there, and you see electric lines of force contract lengthwise so that they explain the attraction between unlike charges. They exert lateral pressure to explain the repulsion. The properties, the first thing is that they are basically purely imaginary lines of force. A unit positive charge placed in the electric field tends to follow the path along which the lines are moving. Electric lines of force emanate they start from a positive charge and they would terminate at a negative charge. the tangent at any point to this electric field lines. So supposing in this upper diagram, if I try to draw tangent, it will be actually in the same line. So that is the direction of electric field. Whereas at this point P, if I try to understand, I draw tangent here and this will give me the direction of electric field at this point over here. So at this point P, the direction of electric field is towards your right hand side. But if I choose this particular point here, at this point the electric field would be pointing in the downward direction. The electric lines of forces, they do not intersect. Fifth point says they do not cross each other. If they do so, then at that point of intersection there will be two tangents. It means that there are two values of electric fields at a point, which is not possible. So you have the electric field lines are not going to cross each other. So you see, this diagram is very important for us to tell you that instead of that, lines will create you see, they will exert pressure on each other. They will just create a pressure between this region. They will separate apart from each other. So then electric field lines of force are closer or crowded in the region where the electric field is stronger. And you see, in this charge Q is here. In this nearby region, you have got large crowding of the electric field lines. So there is a stronger field nearby. Whereas outside, you can consider the electric field lines are well separated. So there is a weaker electric field, you can understand. Then electric field lines of force are perpendicular to the surface of positive or negatively charged objects. So if you have this kind of a surface, the electric field lines which are leaving the positive surface, they will be emitting normally. And even if you have maybe same in this particular case, but if you have a negatively charged surface, the electric field lines will be incident normally on that particular surface. This diagram on the right hand side is very important for us to understand that electric field lines are leaving the surface normally. At this point, if I want to find the electric field lines would be emitting like this. This line is coming here. But these two lines you see are not going to intersect. This line will then move here and this line will then move in the other direction. That's what will be happening. Electric lines of force contract lengthwise to represent attraction between two unlike charges, and to explain the repulsion, they are, you see, exerting pressure. The number of electric lines per unit cross-sectional area perpendicular to field lines is directly proportional to the magnitude of electric field intensity at that particular region. This is basically, you also call it as electric flux per unit area. This quantity, number of electric lines of force incident normally or passing normally through a given area, that's called electric flux. So electric flux per unit area means your electric field intensity. More number of electric lines of force are passing, there will be stronger electric field. Electric lines of force, 11th property says, are not going to pass through a conductor. Hence, inside a conductor, there will be zero electric field. Like here, if I say that I have got a positively charged plate here, negatively charged plate here, in this case, the electric field lines, they will start from positive as seen over here. They will be ending at negative as seen on the right hand side. But these lines, they will not be just passing through here. So these lines are not going to pass through the conductor. When I have positively charged plate over here, these electric field lines, they will be incident over here, which means that this part of the conductor that would be negatively charged. And it's quite obvious that the part of the conductor towards or facing the positive part of the plate, that will have all electrons attracted here. Whereas if you have all electrons on this negatively charged plate, they will repel all these electrons here. So this is what I was actually basically speaking in the first video as you can say inducing charges. So this is what is inducing charges, and overall this conductor entirely remains uncharged with negative charges on the left, positive charges on the right, but there is still not going to be any electric field acting between these two. The electric field lines, they can pass through insulator, of course there is. Now in the next video we will speak about what is meant by an electric dipole and the properties and terms associated with an electric dipole. Okay, thank you very much.